Thank you to first of all, to the organizers for putting together such a wonderful event and giving me the opportunity to speak. My title is up there. What I want to talk about today is a very, very simple thing. It's just using linear algebra, and I'll just write one quick thing on the board. It all started with the following observation. Everything I'm going to tell you starts with the following observation, that if you take this 2 by 2 matrix, 1s01, and apply it to a vector xy, you get x, and then sx plus y, and this becomes shortest when s is equal to minus, and I'm going to write this in a particular way. It's going to be minus y x inverse in some sense. So minus y over x. And I was thinking about this. This is, something that you can teach somebody in high school, and it really, this observation underlies the whole philosophy I want to talk about today. But obviously, I can't spend an hour talking about a 2 by 2 matrix multiplication, so let me tell you what I'm going to use this for. So the outline of the talk, I'm going to talk about something I call, and this is a name that I've sort of newly coined, so if people have objections, they should tell me on historical grounds, something I'm going to call Mauler-Minkowski systems. And this is actually inspired, I should say, by a couple of papers. There's a paper of Donnie's on divergent trajectories on homogeneous spaces and parameter spaces. And then there's a paper of Barak Weiss's, which has almost the same title, Divergent Trajectories on Non-Compact Parameter Spaces. And these two papers have really inspired this, my line of thinking, though I should emphasize that what I'm about to say is much simpler than what's in those papers. Those papers are quite a bit, use quite a bit more machinery, whereas I'm going to just talk about one aspect of them. So what exactly am I going to talk about? What is a Mauler-Minkowski system? So the star player is X, which is a non-compact parameter space of geometric objects. So what do I mean? This is very vague. The example to keep in mind is going to be the space of lattices, of unimodular lattices in R to the n. So you look at R to the n, or R to the d, as I will call it, d for dimension. And you look at a unimodular lattice, that is a collection of vectors who form a basis for R to the d, and the fundamental parallelepiped that they generate has volume 1, and you look at their z-span. So this is z2 in R2, z to the d in R to the d, and any deformation of z to the d by a determinant 1 matrix. So if you don't want to think about anything else, you can just think of X as SLDR, as the space of such objects, which is SLDR mod SLDZ. Why do I say that it's SLDR mod SLDZ? So let me just write one more quick thing on the board. So the canonical example throughout the talk. X equals space of unimodular lattices in R to the d. Now, the group G equals SLDR should act on my non-compact parameter space. It clearly acts on the space of unimodular lattices. If I have some grid in R to the d, and I multiply the whole thing by a determinant 1 matrix, I get another grid. And if my first grid had covolume 1, the second one also has covolume 1. Okay? So I have an action there. And the other thing I want is to each point in my parameter space of geometric objects, I want to be able to assign a discrete set in R to the d in a G equivariant manner. Now, what do I mean by that? Well, I have my assumption is that I have a G action on X, and then I obviously have an SLDR action on R to the d. So when I say G equivariant, I mean if I look at Gx, so lambda sub Gx should equal lambda sub x. So it should equal G lambda sub x, G equivariant. So if I move my points, I move my associated discrete set in the exact same fashion. And For the space of unimodular lattices, the obvious discrete set is the unimodular lattice itself. For technical reasons, I'm going to look at the primitive vectors. I don't want to look at all the vectors. I'm just going to look at the primitive vectors inside. So these are vectors which are not multiples of other vectors in the lattice. And I don't want to include 0. So it's a discrete subset of r to the d without 0. And I'm going to impose two conditions. So I'm going to give you an abstract setup, and then I'm going to give you a lot of examples that fall into this abstract setup. The first condition I call the Mauler condition because it mimics Mauler's compactness criterion for the space of lattices. I want a set in my non-compact parameter space to be pre-compact, that is, its closure is compact, if and only if there's some bound, lower bound, on the vectors in the associated discrete sets. That is, there shouldn't be any short vector in the associated set. So there exists an epsilon naught such that for all x in A, for all v in the associated discrete set, the norm of v is at least epsilon naught. And I'm going to impose what's called the Minkowski condition. This is slightly less crucial, but it will be easily satisfied in all our applications, and it's useful for some later applications, so I've just included it. So for all x in x, there's a constant, so that if you take any convex centrally symmetric set in R to the d of volume at least C, then your discrete set, so this should be a lambda sub x, has a vector in this set. So again, if you're thinking about x as the space of unimodular lattices inside of R to the d, this is satisfied with C equals 2 to the d, right? But my C can depend on the point. Yeah, that's actually going to be important for an application of what are called quadratic differentials. C can depend on the point, but for the space of lattices, you can pick C not to depend on the point. You can pick C uniformly for the space of lattices. Okay, now I've given you a big abstract setup. I should give you some examples, at least, of an abstract setup. If there are no examples, there's no point. So one example, the one I've been saying, is the space of unimodular lattices, which you can identify with SLDR mod SLDZ simply because SLDR acts transitively on the space of unimodular lattices. You give me a unimodular lattice, I can get there from Z to the D using a matrix. And what's the stabilizer of a point? It's simply SLDZ. The stabilizer of the integer lattice Z to the D is simply SLDZ. So if I have a transitive action and I know the stabilizer, I can identify the set of objects with the coset space. The other example, this is something that's very close to my heart, but I may not talk too much about today, is x equals the moduli space of unit area genus G quadratic differentials. So these are flat metrics, singular flat metrics maybe is the best way to think about them, on a genus G surface with cone-type singularities and transition maps of the form z goes to plus or minus z plus c. Let's not worry too much about this other example. I just want to let people know that it's there. This is the context. This is, for instance, the point of this is that you can, in the same way, treat both these cases. I'll get to that. So what is lambda x? What is the associated discrete set? It should be GZD prim for the space of lattices. I want to only consider primitive vectors. It's not going to make a huge difference, but if I want to throw away 0, I should consider primitive vectors. For the set of quadratic differentials, I associate what are called the holonomy vectors of saddle connections. A saddle connection, so if I have a flat metric on a surface of genus greater than 1, it can't be non-singular. It has to be singular. And a saddle connection is a geodesic with respect to my flat metric connecting two singular points. Now, there's a well-defined notion of a holonomy vector, which is just integrating the form, just basically integrating the metric along this geodesic, and you get a vector inside of R2. You get a complex number, which you think of a vector inside of R2. So you get a set inside of R2. And here D is 2. You have an SL2R action, and this is an SL2R equivariant assignment. What are some other examples of these things? It would be bad if I only had two. I could look at SLDR semi-direct RD to the K mod SLDZ semi-direct ZD to the K. This would be if I took a lattice and I took K independent translates of it. And I looked, and now my associated discrete set would, again, I would just draw the lattice and then its K translates. That's still a discrete set. It's a union of K translates of a discrete set. Similarly, I could mark a bunch of points on my quadratic differential space, and I could ask for geodesics in between those guys would be my associated discrete set. Another one, which doesn't quite fit into the framework, but you can make it work, is SL2R mod gamma when gamma is a non-uniform lattice. When gamma is a non-uniform lattice, you look at how gamma acts on R2. Gamma is a group of 2 by 2 matrices. It can act on R2. The fact that it is non-uniform guarantees that there is a discrete orbit. There's a vector v in R2 so that gamma v is discrete. This is coming, for those of you who know, from the closed horocycles that define the cusps. So I want gamma to be finite volume, but non-compact. And what I can look at, let's just assume that there's one cusp, and let's pick one discrete orbit, gamma v. I can associate to G gamma the discrete orbit G gamma v. And that's a nice assignment. That's an equivariant assignment. And having a short vector in G gamma v is exactly telling me that I'm on a very short horocycle on my hyperbolic surface. That is, I'm very far out into the cusp. There's some inverses and transposes if you want to get it absolutely right with row vectors and column vectors. But basically, it's G gamma goes to G gamma v. I'm not going to spend too much time talking about these three examples because I want to focus on just SLDR mod SLDZ for the most part, just for the purposes of time. But all of these have some characteristics of negative curvature. This one in particular has the most negative curvature. It's actually negatively curved, SL2R mod gamma. But the dynamics I'm going to talk about has a lot of flavors from negative curvature. Okay. So now what's my question? I've given you a setup, this Mauler-Minkowski setup, a lot of big words. Now my setup is I have this group acting on this parameter space of geometric objects. I take some subgroup, my favorite subgroup, and I take a point. And now I look at its orbit under this subgroup. And this might be going, it might be living in some small part of X. It might be going everywhere in X. I would like to know how it visits the non-compact part of X. Pretty much every project I've thought about is about some version of this question. How does the orbit of a subgroup of an ambient group action visit the non-compact part of a parameter space? And I want quantitative information. I don't want to say, well, it goes there. So I don't want to just say, for instance, that Lx is dense. And so, yes, it visits the non-compact part. I would like to say, let's look at some big subset of Lx. How far has it gone into the cusp? Okay. So to do that, I'm going to need to make a couple of more definitions to state my general theorem. I'm going to relate how orbits go into the cusp to a general notion of a Diophantine exponent for a discrete set. Now, just as a disclaimer, I'm not an expert in Diophantine approximation. I don't know whether this notion of Diophantine exponent for an arbitrary discrete set has been defined. It probably has, but I just sort of naively extended the standard notions of Diophantine exponent in the following way. So now I take a discrete set in R to the D, and now think about D as being at least 2. And write D as m plus n, where m and n are integers. And so now we break up R to the D as R to the m cross R to the n. And I want to think of R to the n as the vertical direction and R to the m as the horizontal. If you want, you can think about D equals 2 and m and n as 1. And a lot of this may be a little clearer then. I say that nu in R is an mn exponent of lambda if there exists a sequence of vectors in my discrete set lambda who start to approximate the vertical. So this is saying yk over xk is going to infinity. So they're coming closer and closer to approximating the vertical, but not only that, they're doing it at a certain rate. They're doing it at this rate nu minus 1. x is actually smaller than y to the minus nu minus 1. Now, this is really only interesting for nu positive. But, so this is, anything that satisfies this is called an exponent. But I want to associate a number to a discrete set. I want to associate an actual notion. So I let exp mn to be the set of mn exponents, possibly empty, right? I mean, if I don't have anything that approximates the vertical direction, this could be empty. Obviously, I will want to rule that out. The Minkowski condition, for instance, will immediately rule that out. You will immediately be able to construct guys that approximate the vertical because of the Minkowski condition. And you define mu mn to be the supremum of this set. Okay, so this is the best possible. Notice, just go back here, I don't claim that necessarily there is some guy, I can't necessarily replace nu by mu there. Mu is just the supremum of the guys where I can do it. I might not be able to do it with mu. The existence of any vertical approximants means that 0 is, so as long as I have a sequence where y over x goes to infinity, as if I approximate the vertical, means 0 is an exponent. And the Minkowski condition implies that d over m, or m plus n over m, is actually an exponent. You can actually approximate with it. And the way to do that is you just take, as your convex set, the product of balls in Rm and Rn of the appropriate sizes. Of, let's say, 1 over, you can do an appropriate calculation, and you can get this to come out as your exponent. So this is always in it if your lambda satisfies the Minkowski condition. That is, there's some number so that every convex centrally symmetric set that's big enough, bigger than that number, has points from your set, then you're guaranteed that m plus n over m is an exponent. A generic two-dimensional lattice, the exponent will be 2. The 1, 1 exponent will be 2. It will be exactly this, exactly. Right? This is basically Khinchin's theorem in that case. Yeah. Now I want to talk about, sorry. So this is a lot of information to process. I realize that. Think, if you want, just about lambda as lattices. The nice thing about this approach is that it'll work for other types of discrete sets, but for now, just think about lambda even as a two-dimensional lattice. Think about m equals n equals 1, d equals 2. And for a two-dimensional lattice, most of the time, you'll just get 2. You always get 2 in there, unless you have a vertical vector. Let's avoid that for now. So now I want to state a theorem. Just in this very general abstract setup. The point of being able to state the theorem in the abstract general setup is then one can just harvest like grapes corollaries about all these different examples. They all come for free from this theorem. The price you pay is that at first it's a little bit hard to care about the abstract theorem. But let me soldier on. I want to define a norm on R to the d. My norm, and the norm isn't so important, it's just useful for calculations because in the end we're going to take logs of norms and things will go to infinity. But let me just be careful and define the norm first. I think of R to the d as R to the m cross R to the n. And I write a vector v as x, y, x in R to the m, y in R to the n. And I take the supremum of their two norms. So I just think of these, I take the supremum of their standard Euclidean norms. So if, again, for m equals n equals 1 and d equals 2, this is the sup norm, just the sup norm on R2. Okay? So you can think of the sup norm on R2 if you like. Now, for any old discrete set, I define alpha 1 to be the supremum, well, again, discrete and avoiding 0. It should be an R to the d minus 0. I don't want this to be infinite. I define alpha 1 of the discrete set to be 1 over the length of the shortest vector. Okay? Sup of norm of v to the minus 1. Standard definition, right? For a lattice, 1 over the length of the shortest saddle connection is a very important function on the space of quadratic differentials. This will also measure log of the length of the shortest length of the closed Horus cycle you're on in SL2R mod gamma. It's all of those things. And what we're going to do is we're going to measure our quantitative rate of escape, our visits to the non-compact part of the space, in terms of alpha 1 and log of alpha 1. Okay? Log alpha 1 is what's more traditionally used because then you can play around and use your favorite norm to define alpha 1 when you use log, because any two norms on this finite dimensional space only differ by a constant. Okay. So the Mauler condition on X, so now if I go back to my parameter space, if I define, just by abusive notation, alpha 1 of X as alpha 1 of the associated discrete set, it implies that that function is unbounded off compact sets. In particular, this sequence is a CR of the set of guys of sublevel sets of alpha, should be less than or equal to really get a compact set, is an exhaustion by compact sets, or by pre-compact sets at least. Now, okay, so this is how I'm going to measure going to the non-compact part. I'm going to use alpha 1 to measure how to go to the non-compact part. I mean, otherwise in my setup, I don't know what quantitative information is, right? All I know is that vectors go to 0 off the compact part. So I have to use something about those vectors, and I use their length. Right? The length of the vector tells me how far I am, how close to infinity I am. And now let me talk about the particular subgroups I'm going to use. I'm going to think about two very specific subgroups. One is a diagonal subgroup. So I look at the identity matrix with m entries and then the identity matrix with n entries, and I weight them with this e to the nt over d and e to the minus mt over d. I think I got this right. This is a determinant 1 matrix. It's an SLDR. It's a 1-parameter subgroup. And then I'm going to look at the following bigger subgroup, higher dimensional subgroup. So this is a m times n dimensional subgroup. It's the set of matrices that look like this, IM0 BIN. And I'm going to call that matrix H sub B, where B is any old matrix, n rows and m columns. Okay? This matrix is, in fact, this subgroup is horospherical for this 1-parameter diagonalizable subgroup. What does that mean? It means the following thing. If you look at GT, if you conjugate HB by GT, so GT, HB, G minus T, you get H e to the minus TB. That's why I picked these funny numbers here, NT over D minus MT over D. So this is the crucial relation. Now I'm going to define a subset of my big group H. I'm going to call it BS, which hopefully is not the subject of this talk. HB, it's all the matrices with norm less than or equal to S. And just notice that the above relation means that BS is actually, you take B1 and it's just, you translate it by, you conjugate it by G minus T, and you're getting these bigger and bigger subsets of your subgroup H. So now the question I'm going to look at, the most precise question I'm going to look at is I'm going to start with the point X, and I'm going to look at the orbit under BS. And so this will be some big chunk, and I want to know what's the farthest that has gone into the non-compact part. Similarly, I'll look at it under GT and ask, how far is it in the non-compact part? That is, given X and X, we're going to define two quantities. These are about the excursions of the orbits under these subgroups. One, beta S, which is the supremum over all the guys in BS of log alpha 1 of h lambda x or lambda sub hx. It's the same thing because of equivariance. And similarly, gamma t of x is log alpha 1 of gtx. Okay? So beta S is telling me how far this big leaf, I can think of it as this high dimensional thing, what's the worst it's gone in? How far has it gone in? And gamma t of x is telling me at this particular snapshot in time, how far is this particular orbit in the non-compact part? Okay. So what's the statement of the theorem now? What can we say about beta and gamma? So I have alpha, beta, and gamma. What can we say about them? Okay, so this is recent work. It's not quite written up yet in tech. Hopefully it'll be posted to the archive soon. So let Gx be a Mauler-Minkowski system. Let D equals m plus n, GT, be as we've defined. Take a point in X and suppose the associated discrete set doesn't have any vertical vectors. That is, nothing in just the Rn direction. Nothing like 0 cross Rn. Then you have the two following things. You have the lim sup as s goes to infinity of beta s of x over log s is 1 minus 1 over the mn exponent of the discrete set. Now notice m and n you're allowed to vary. So even for a lattice, as you vary m and n, you get different pieces of information, which is not surprising. You're looking at different subgroups. As m and n change, the subgroup changes, and the exponent could possibly change. And the second thing is not so much a theorem as something that's just a restatement of something that's pretty well known. It's almost a restatement of the definition of Diophantine exponent. Is that lim sup of gamma tx over t is m over d minus 1 over mu mn of lambda. In particular, these quantities are the first quantity is n over d plus the second quantity. And again, an important note, for the Minkowski condition guarantees that mu mn of lambda is at least d over m. So the second quantity is always positive. And the first quantity is also always positive. So in particular, the horospherical guy goes into the cusp at some logarithmic rate. Its worst behavior to the cusp is at a logarithmic rate. And that logarithmic rate is governed by the linear rate of escape of this associated one-parameter guy. Most of the time, as we'll see when I make some remarks about the history of this thing will be 0. Most of the time, this thing will be 0. And thus, this first quantity will be n over d most of the time. Let me just make a couple of remarks about what this is useful for, what one application is. So the point is this simultaneously addresses, and you can simultaneously generate theorems about the space of lattices, about the space of quadratic differentials, and SL2R mod gamma. And spaces of marked points on lattices, marked points on quadratic differentials, all sort of get treated at one fell swoop. The other selling point behind this is, notice I haven't used the word ergodic even once yet. There is no ergodic theory in this proof. There is no Borel-Cantelli lemma. There is nothing. There is just this observation that I wrote down at the very beginning. There is only linear algebra. This is literally only linear algebra. You give me a week, and I can explain this to your linear algebra students. Maybe more than a week, but this is only linear algebra. Okay. What are some applications? What are some corollaries? One nice one that I'm fond of, and this is something that grew out of some joint work with Professor Margulis, is the following. Take a matrix, an m by n matrix now. I'm going to define its Diophantine exponent to be the supremum of nu in R so that I have a good approximate solution in integers to AQ equals P. I have AQ minus P is less than or equal to the norm of Q to the minus nu minus 1. And here the norms, let's say, are standard L2 norms. Okay? So I have an approximate integer solution. So let me write this down. An approximate solution to AQ equals P. A is any old matrix, very irrational. And I might want to ask an approximate solution to AQ equals P. And you should think of A as M, A is giving you M linear forms in n variables. And I'm asking, put in some integers to this. And how closely can I approximate other integers using m linear forms in n variables? The theorem is as follows, and this is a very old set of ideas to use this kind of matrix to study the Diophantine property. Yeah. 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 It's this -1 is just to make it match up with the Diophantine exponent for a number, because there you have a q. If you think of a as just a number, an irrational number, then this is just the best a minus p over q less than q to the minus nu, right? If you divide this expression by q. So let's look at this lattice. Im minus a0 in z to the d. Again, I think I got the sizes right. I checked that carefully. And now you look at lim sup of this beta s of this lattice and divide by log s, it's 1 minus 1 over the Diophantine exponent. And the second thing is well known. This is pretty much the definition of the Diophantine exponent. So I just put it there for context. It's m over m plus n minus 1 over mu of a. Generically, the Diophantine exponent of a matrix will be m plus n over m. This is the Khinchin theorem. But you can have exceptional behavior, any kind of exceptional behavior you want, bigger than that. Just as a note, for n equals 1, this calculation will appear in a forthcoming paper with Professor Margulis on, which I'll mention a little bit later when I talk about the history of the subject. Okay. So, yeah. So let's just leave this theorem up for a second. This is where it started in some sense. The n equals 1 we worked out because we were interested in working out an example for how horospherical subgroups go into the cusp in general G mod gamma. We have a theorem about that, but we wanted a concrete example. And so we looked at SL dr mod SL dz, and we said, look, we can relate it to Diophantine exponents of vectors in one lower dimension. And then I realized that one can do this for matrices. And then I realized as I was doing it, I didn't really rely on the fact that what I was using were lattices. And that the same approach could work for any sort of discrete set. So this is somehow the theorem that got me started thinking about the more general setup. And the general setup seems to work nicely in many different cases. So now, the setup wasn't created out of whole cloth. People have been thinking about how trajectories of how orbits of actions go into non-compact parts of spaces for a very long time, for at least, probably goes back to art and at least 100 years, or Poincaré even, if you want to. But for me, a lot of the interesting parts of the subject, I got started in grad school. I read this beautiful paper of Dennis Sullivan's, where he was interested in the following very geometric question. Take a non-compact finite volume hyperbolic manifold, and you look at the geodesic flow. A typical geodesic, we know that the geodesic flow on this object is ergodic. First time I'm actually using the word ergodic in the talk. In particular, that means a typical trajectory is dense. It goes everywhere. It goes, in particular, into the non-compact part, into the cusp. And what does it do? It goes into the cusp, it comes back, it goes further into the cusp, it comes back. How does it go into the cusp? Sullivan proved a beautiful theorem called the logarithm law, and as far as I know, he coined this term, though I'm not quite sure about the history. At least in dynamics, I don't know whether other people had used this term before Sullivan, but law of the iterated logarithm, right? So, but this isn't log, right? It's log now. So Sullivan, as far as I know, coined this term in the context of dynamics. I won't state his theorem fully because I'd have to write down a lot of notation about hyperbolic manifolds. What I'll do instead is I'll give an example of his theorem generalized in the context that we've been thinking about today. Kleinbach-Margulis in 1999 generalized this to symmetric spaces. An example theorem in our context is the following. let AT be a one-parameter diagonal subgroup of SLDR. So for instance, that subgroup GT that I put up earlier. So you can think of just some e to the t's along the diagonal. For almost every starting point, for almost every lattice, and almost every with respect to the Haar measure on the group, the lim sup as t goes to infinity of log alpha 1 of gtx over log t is 1 over d. Sorry, AT. Yeah, it's AT. Yes, that's right. So that's the remark. So this, going back, as Uri points out, let's see, going back to the main theorem, there was this gamma t was basically log alpha 1, right, of GTX. And now I'm dividing by a t. So what Kleinbach-Margulis, or what Sullivan and what Kleinbach-Margulis tell us is that this thing, and this should be a t, I'm sorry, should be 0 most of the time. Because the correct thing to divide by almost everywhere is log t. So if this thing is 0 most of the time, then we have some information about this most of the time as well. Let's get back to the history. So this gives you some information about the generic system as well. For SL2, actually, for SL2R mod SL2Z, you can recover this theorem from Khinchin's theorem, actually, in some sense. So that's maybe the earliest version of this logarithm law is due to Khinchin. Okay. There are other logarithm laws due to Howey-Maser on the Teichmüller geodesic flow, on this context of quadratic differentials that I had mentioned earlier. The diagonal flow is called Teichmüller geodesic flow. There's a theorem of Hersonsky and Paulin on general tree quotient. So you take a tree, a locally finite tree, and you take I think, geometrically finite lattice, non-uniform lattice in the automorphism group, and you look at the quotient, and then you look at the behavior of a typical geodesic, and it satisfies the logarithm law. And then in a long delayed paper, which hopefully will come out this fall, myself, Anish Ghosh, and Amritanshu Prasad have one for geodesics in buildings as well. Okay. But there were two parts to the main theorem. The main theorem had both this linear, this diagonal flow part, but it also had these unipotent matrices, IM, IN, had these guys with these ones down the diagonal. And none of the theorems up here have ones down the diagonal. All of them have e to the t's down the diagonal for the orbits that one is considering. So what about unipotent flows, or more generally, unipotent actions? And an important thing, so above results are for diagonal flows. Unipotent flows behave very differently in many ways. And I'm going to brush 30 or 40 years of very interesting research under the carpet in one slide by doing non-divergence in one slide. One important difference between diagonal and unipotent flows is whereas for a typical orbit of a diagonal flow, you can't say much about, well, all the time, any big piece is inside the compact part for most of its life. You can say that for a unipotent flow. Diagonal flows can be very wild. They can do anything you want them to. But unipotent flows are much more well-behaved. Informally, any big piece of any orbit of a unipotent flow spends most of its time in a compact set. For our setting, if you have a unipotent flow on a non-compact parameter space, at least the examples I've shown, any big piece of orbit spends most of its time in a compact set. And this is due in various beautiful papers to various combinations of Dani, Margulis, Kleinbach, dating back to the early work in the 70s to a lot of work in the 1980s. In the context of quadratic differentials, or in the Teichmüller theory context, this is due to Yair Minsky and Barak Weiss, inspired by Kleinbach and Margulis. And a lot of this uses what's called the linearization technique. They also study how to go into the non-compact part by looking at vectors, and they say, if you have a short vector, at one time it has to grow. It has to get a little bit longer relatively quickly. And again, I feel very bad because I'm brushing 30 years of really great research away in one slide. But yeah, and next time I'll give a survey talk on non-divergence, make up for it. So there is an interesting similarity, though. So I was just saying, unipotent flows, diagonal flows, very different in many ways. But in this strange way, if you measure their worst behavior into the cusp, at least in this context, they're similar. So this is a theorem that I proved with Professor Margulis in 2008, is if you take a unipotent one-parameter subgroup of SLTR, then again, for almost every starting point, lim sup of log alpha 1 of USX over log S is the same thing, 1 over D. The key point is, let me just go back to the main theorem here. The spiritual reason behind the fact that these are the same is that the unipotent flows excursion to the cusp is not governed by the typical behavior of a geodesic, but by the worst behavior. And the worst behavior of the diagonal flows is linear. And yeah, so that's for those, this is just a cryptic remark. We also have some results about horospherical actions, as I mentioned before, in a forthcoming paper. Okay. So let me say in my remaining 5 minutes a few words about the proof. The proof, the big picture of the proof is there's a very abstract theorem on discrete sets and Diophantine exponents in these lim sups that makes no reference to parameter space at all. All you need is a discrete set in R to the D and these matrices. And you manipulate your discrete set by these matrices, and you see what happens to vectors. And this is just completely linear algebra. And then the Minkowski condition on the parameter space ensures that the crucial condition, or that some conditions in the abstract theorem are satisfied. So the Minkowski condition guarantees you that you have something in your Diophantine exponent set. Otherwise, you may not have any approximates at all. So, and then you have to verify the Minkowski condition in practice for your parameter spaces for the various examples to check, well, Minkowski's theorem verifies Minkowski's condition for the space of lattices. For quadratic differentials, there's a geometric argument that's not too different from the proof of Minkowski's theorem in dimension 2. This is not written down anywhere actually, but it's verbal discussions with Yitwa Chung. Yair Minsky and I concocted an argument in his office. I think Pascal Hubert and Howie Mazer have their own arguments. It's all basically the same argument. There is a nice geometric argument that guarantees it. We'll probably just put it down for completeness sake in the forthcoming paper. Okay. Let me give a flavor of the proof. Let me just give one little chunk of the proof that's enough to give you a flavor. So let lambda be a discrete thing satisfying the Minkowski condition. Let beta of lambda be the lim sup of beta s, so this orbit under the horospherical thing, divided by log s. We'll show that beta is at least 1 minus 1 over mu by showing you give me any exponent, I'm at least 1 minus 1 over nu. Okay? So if I'm bigger than 1 minus 1 over nu for any exponent, I'm bigger than 1 minus 1 over the sup. 1 minus 1 over x is an increasing function of x. It took me a long time to figure that out. Okay, so what am I guaranteed? I have my set lambda. I have an exponent nu. That means there's this sequence of guys in my set so that xk is less than yk to the minus nu minus 1. Okay, that's just the definition of nu being an exponent. I have these good approximates. Let's write down y very explicitly. So y is a vector in Rn. So let's write down its components, yk1 to ykn. Now I'm going to define a bunch of vectors. By their name R, you can see that they're going to be rows of something. The ith row is going to be the ith entry of y times xk, the xk is a vector now, divided by the norm of xk squared. So a couple of things to know. One, the norm of RKI is YKI over XK. Right? That's just easy calculation. The more crucial thing, how did a dot get on top of XK? Okay. RKI dot XK, not XK dot. So when I take the inner product of RKI and XK, I simply get this value, minus YKI. Right? Because XK dot XK is just the norm of XK squared. That goes away. Great. So these are some vectors with some nice properties. So now I make my matrix B to be the matrix with these guys as my rows, RK1 through RKN. So B has n rows and m columns. The R's are in Rm. Right? Now notice the L2 norm of B is just YK over XK now, right? Because the L2 norm of the ith row was YKI. Add them up, I'm taking the L2 norms, I get YK over XK. And let's call that thing S sub K. Okay? So we'll call that S sub K in a second. And now notice the HBK, now this is that thing I told you about in the very beginning. 1S01 xy is x sx plus y. X, bk, xk plus yk. And I've engineered bk so that bk, xk plus yk is 0. It goes away. So now I have this vector. I have a short vector. This is my candidate short vector at this time. So sk, there should be an equals sk. I guess it didn't compile properly. Equals sk. So this is the, it's at some, I've stretched it. So clearly, alpha 1, the 1 over the length of the shortest vector, is at least 1 over the norm of xk, right? I have this vector 0 xk. So that vector has norm xk. So 1 over norm of xk is as, short. But now xk is less than or equal to c times yk to the minus nu minus 1. Right? There's some constant. Which means, rewriting this, 1 is bigger than or equal to, forget the constant for now. Just think about xk to the 1 over nu, yk to the 1 minus 1 over nu. And when I divide by xk, I get yk over xk to the 1 minus 1 over nu. I replace the 1 in the first inequality by what's on the right side there. And so I get alpha 1 is at least this constant times sk to the 1 minus 1 over nu. Now take logs and divide by log sk. You'll get on this side, there'll be some term involving the c, which I don't care about because sk is going off to infinity. And here I'll get 1 minus 1 over nu. Here I'll get log alpha 1 over log sk, as desired. So I'll have the sequence of times going off to infinity where I'm at least 1 minus 1 over nu. Now, the other parts of the proof are similar. You have to do some linear algebra calculations and basically make a dictionary between your lim sup being something and having a sequence of approximates. I suppose one shouldn't say this about a talk one's giving, but it's almost tautological in some sense. Once you start working it out, but the amazing thing is, from nothing, you're getting interesting information, or at least information that I find interesting, on cusp excursions, on parameter spaces, in a variety of contexts, in 4 or 5 different contexts, just using the same idea, the same simple linear algebra, you're getting non-trivial information about how orbits go into the cusp. Non-trivial quantitative information, almost out of nothing. That's it. Thank you. Sure. Yeah, so what Uri is saying is, for almost every point, I have some dynamical information usually about gamma t. And then I can get some information about the exponent using the theorem. And then I go back and plug it into the first equation, and that tells me something about how the Hora cycle has gone into the cusp. And that's, I mean, yeah.
The upshot is that you get new information about unipotent explosion.
Yes.
Because of the
Yes. The upshot is that this, I mean, the practical upshot is this gives you a concrete relation between the unipotent and diagonal cusp excursions that works in a variety of contexts. We usually know something about the diagonal cusp excursions, and then this translates you and says, look, the unipotent is completely governed by the diagonal, which is, yeah, not that surprising because it forms some set of the stable manifold. It's really the stable manifold here that we're looking at to look at in the dynamical language. The other upshot of this is, I mean, in fact, for quadratic differentials, I don't think anybody had thought about this particular setup before. People have thought about Diophantine exponents in some setting, but it actually has some nice interpretations for quadratic differentials. But that's a whole different, I could tell a whole story just focusing on this theorem for quadratic differentials. But yeah, the upshot is that you know something about the diagonal flow, you get information basically for free about the unipotent flow. Yeah. No, no. No, so unfortunately the theorem it would be nice if we could, but the theorem with Margulis is on one parameter unipotence, not these big Hora spherical subgroups. So one weakness that I've sort of swept under the, yes, for n equals 2 it does, but one weakness that I've swept under the carpet is that this is only dealing with big unipotent subgroups, Hora spherical subgroups, not one parameter is my method. The Kleinbach-Margulis, the result I proved with Margulis relies on a theorem about geometry of numbers, sort of a random Minkowski theorem, and uses the Borel-Cantelli lemma and ergodic theory. Yeah, it would be very nice if we could recover that. Yeah, so this is actually a thing I would like to do next, or I would like somebody to think about, is how to get information about cusp excursions for one parameter, unipotent things on general G mod gamma. I don't know how to do that in general. Or, yeah. So. Right, right. So let's go back to the main theorem just 1 second here. So when I first started talking about the subject of unipotent cusp excursions with Professor Margulis, his guess, and sort of a good guess, was that it would be log-log. Right? Would be because the unipotent, because the diagonal flow typically escapes at logarithmic rate, or visits the cusp at a logarithmic rate. And anything the diagonal does, you expect the unipotent to do, except at a 1 log slower. Right? So you should expect maybe log-log. But what happens here is what's really, in some sense, what's going on here is you have this big piece of the unstable manifold. And this guy's going into the cusp. You measured the linear rate at which this is going into the cusp, and that tells you information about the logarithmic rate at which this does. Because you can always stitch together sort of a backward time trajectory on the unstable manifold to do whatever you want. This is the stable manifold for GT T positive, but it's the unstable for T negative. So you're allowed to do anything you want T negative on a big piece of orbit. For T negative time, you can do anything you want. And it's that worst behavior. You can pick a divergent GT trajectory. And that divergent GT trajectory is what's giving you this log S here, not log-log. The typical geodesic would have given you a log-log, but the divergent guy is giving you a log. So that's the essence of the cryptic remark.